Hello, I'm Shweta, and today I will discuss our work, Scoped Buffered Persistency Model for GPUs. Let me start with a brief summary of our work. A prior work GPM shows how many GPU applications can benefit from the persistence provided by persistent memories. However, GPM does not define a persistency model for GPU programs. We also find that traditional CPU persistency models do not scale well for GPUs. To address this gap, we propose a persistency model which is optimized for the GPU's highly parallel architecture. Non-volatile memory technologies, such as Intel's Optane DCP-MEM, blur the long-held distinction between memory and storage by enabling fine-grained persistence through load-store instructions. NVMs support lower read and write bandwidth compared to volatile memories. We refer to NVM accessed via load and store at byte granularity as persistent memory. Although Intel is discontinuing Optane PM, Samsung has launched memory semantics SSDs that can effectively act as PM. Additionally, the Compute Express Link 2.0 specification incorporates a GPU persistent flush operation for manipulating PM resident data structures. Hence, while Intel's Optane is the first commercially available PM, it's unlikely to be the last. In our previous work GPM, published in ASPLOS'22, we demonstrated how GPU kernels can directly access PM without requiring any hardware modification. This enables many GPU-accelerated applications to benefit from the persistence provided by PMs, including GPU-accelerated persistent key-value stores and faster checkpointing of long-running DNN kernels. Ensuring recoverability of data structures is a fundamental requirement for any PM-aware program. Writes to PM resident data structures from different threads can be cached in volatile caches and drained to the PM in an arbitrary order. A crash can thus leave PM resident data structures inconsistent. While GPM demonstrated the benefits of PM for GPU programs, it does not specify a persistency model, making it difficult for programmers to reason whether a GPU program will correctly recover after a crash. Persistency models define the ordering in which writes to PM, aka persists, become durable. We refer to this order as persist memory order or PMO. A model determines how programmers can express PMOs both within and across threads. While there has been a plethora of work on designing persistency model for CPUs, we focus on designing a persistency model for GPUs. We propose to formally define a GPU persistency model which conforms to the GPU's memory architecture. A GPU persistency model should also scale well across concurrent GPU threads while bridging the gap between GPU's bandwidth requirements and the lower bandwidth provided by PMs. We find that CPU persistency models are not well suited for these goals. We shall now discuss some unique challenges in designing a GPU persistency model. Firstly, unlike CPUs, the GPU's hardware is not responsible for keeping its L1 caches coherent. Hence, unlike CPU persistency models, we cannot rely on coherence messages for tracking inter-thread ordering dependencies. Secondly, CPU persistency models rely on global ordering of persists, which is not well suited for the GPU's highly parallel architecture. Furthermore, GPU applications may require PMO both within and across thread blocks. Hence, only globally ordering persist is not just expensive but also unnecessary. Finally, GPU programs require very high bandwidth and issue persists in bursts. However, as PM offers lower bandwidth than what is demanded by GPUs, buffering of persists is necessary for GPU kernels. While CPU persistency models propose buffers for performance, traditional CPU persist buffers do not scale well for GPUs. Sharing a single buffer across all the SMs is not feasible and makes it almost impossible to track ordering across persists. Alternatively, a per-thread buffer would incur massive hardware overheads due to the hundreds of thousands of concurrent GPU threads. It also makes the detection and enforcement of inter-thread PMO intractable. To summarize, CPU persistency models are not well suited for GPUs because 1. In the absence of coherent L1 caches, GPU models cannot easily communicate inter-thread PMO. 2. Global communication of persists is expensive and often unnecessary. 3. Naive extension of CPU persist buffers is impractical for GPUs. Therefore, a formal GPU persistency model that caters to the GPU's unique architecture is essential for high-performance computing. To this end, we propose Scoped Buffered Release Persistency or SBRP. We provide persist acquire release operations which help the programmer to explicitly define the inter-thread PMO as shown. Thus, we do not depend on coherence messages for tracking inter-thread PMO. We borrow existing offense and defense operations for intra-thread PMO. Next, to avoid globally ordering persists, we take cue from the GPU's memory consistency model. A GPU program arranges hundreds of thousands of concurrent threads in a hierarchy. It uses scopes to allow programmers to specify the subset of threads that would participate in synchronization. We posit that GPU persistency models should similarly support scopes to specify and enforce inter-thread PMO. In the example shown, threads within a thread block issue block-scoped acquire-release operations for ordering. We finally propose a novel GPU persist buffer that allows us to bridge the gap between GPU's bandwidth requirements and the bandwidth supported by PMs. We add a persist buffer per SM. Let us now take a deeper look within each SM to see how these unique buffers work. The buffers are closely coupled with the Elvin cache. Each buffer entry contains three fields. The first is a type field, which indicates whether the buffer entry is for a persist operation, a fence operation, or a scoped acquire-release operation. The second field, the Elvin cache index, is only used for persist operations and identifies the cache line containing the data for the entry. The last field, the warp bitmask, identifies the warps that executed the operation. Further details on how these entries are merged and what happens when multiple warps share cache lines can be found in the paper. We employ this buffer in tandem with the GPU's warp scheduler to enforce the programmer's indicated PMO. For example, the defense operation necessitates that all previous persists be durable before execution can be proceeded. When a warp persists px and then another warp persists py, the warp is descheduled when it reaches the defense and is not scheduled again until its defense operation is at the buffer's head. Now let's examine how inter-thread PMO is enforced. First, a warp persists px and releases it. Then another warp acquires and persists py. Assuming that the second warp tries to evict py before px is persisted, violating the PMO. The second warp is descheduled until the prior data is persisted, guaranteeing that the PMO is ensured. A key performance consideration while designing the buffers is deciding when to flush dirty PM cache lines. One option is to eagerly flush all persists. While this ensures that the NVM bandwidth is utilized well, it reduces the opportunities to coalesce in the cache. GPUs coalesce writes to the same cache line to reduce the number of write packets drained from cache to memory. On the other hand, lazily flushing persists at an ordering operation leads to poor utilization of NVM bandwidth as it overwhelms it and could potentially cause stalling of future persist flushes. We rather propose a window-based policy to get the best of both worlds. Each SM tries to maintain a fixed number of outstanding persists, creating a stream of persists, while allowing coalescing opportunities. To summarize, we propose SBRP, which utilizes scoped acquire-release operations to dictate PMO across threads, allowing it to scale effectively across hundreds and thousands of concurrent GPU threads, while adhering to the GPU's existing memory architecture. Finally, we propose a novel persist buffer design for GPUs that efficiently implements all types of PMO. Let's now look at the simulated platform and the results we obtained. We evaluated SBRP by extending GPGPU Sim 4.0. The following table lists the simulated configuration. We evaluate 6 applications shown in the table. Each application places its key data structures in the PM for recoverability. These applications have different types of PMO like intra-thread block, and inter-thread block. We compare SBRP against GPM. GPM allows GPU kernels to access PMs directly. A system scope thread fence is used to dictate ordering boundaries. We find that GPM follows a scope-agnostic, unbuffered persistency model. The model is similar to CPU's epoch persistency model as it employs system scope fences that act as epoch barrier and globally orders all persists. SBRP not only defines a persistency model that helps programmers in reasoning about the intra-thread and inter-thread PMO, but also improves performance. On average, SBRP improves by about 2.7x over GPM. Reduction greatly benefits from SBRP. This kernel leverages intra-thread block PMO, which benefits from SBRP as the persist remains in the L1 cache without being flushed to the PM. It speeds by up to 3.5x over GPM. Refer to our paper for a more detailed evaluation. To summarize, we propose scoped buffered persistency models that support scoped acquired release operations for dictating PMO and supports buffered design specifically for GPUs. Our artifact is open source and has received all the badges. Thank you.